High-performance athletes share the essential characteristic of competitive endurance with the intention to exercise beyond the limits of endurance capacity. When athletes present any pain or symptoms, these are usually considered to be caused by the exercise. This as well causes that some diseases are being undiagnosed and could end the athlete's career. One type of undiagnosed disease is arterial endofibrosis. This is a vascular pathology that affects athletes. It is defined as a fibrosis leading to wall thickness and reduction of the artery's diameter. As studies estimate the prevalence of arterial endofibrosis to be as high as 10 to 20% among elite performance athletes, the aim of this study is to perform a model simulation on an open-source software to explain the blood flow of this disease and the level of complexity that it represents in diagnosis.
There were made three simulations. The first one was a computational fluid dynamics to obtain the pressure exerted on a healthy artery and the wall shear stress. The second one was a finite element analysis of an endofibrotic artery in order to obtain the geometry deformation. And the third one was another computational fluid dynamics to compare the results obtained in geometry 1 and 2. All simulations were made in the solid modeling computer-aided design software SolidWorks 2019, developed by Dassault Systems. A new material was defined in order to get a similar material to the external iliac artery with the following properties: a Young modulus of 160 kilopascal, a Poisson ratio of 0.49, a mass density of 1020 kilograms per cube meter, a tensile strength of 1 megapascal, an ultimate strength of 1.38 megapascals. The geometry has the following characteristics: an inner diameter of 12.66 millimeters, a wall thickness of 1.78 millimeters. We use a flow of 8 liters per meter, and an arterial blood pressure of 200 millimeters of mercury, plus the atmospheric pressure. The first simulation was a computational fluid dynamics. The aim of this simulation was to obtain the wall shear stress and the pressure on the healthy artery wall. The geometry shown in the slide has the same dimension as we mentioned before and a length of 200 millimeters. We define a new fluid that has the same properties as real blood, which are the following: a viscosity of 3 millipascal seconds, and a specific heat of 3.49 kilojoules per kilogram Kelvin, a density of 160 kilogram cube meter, a thermal conduct of 0.52 watts per meter Celsius. As a result of the CFD study, the model of this simulation presents a wall shear stress of 60.26 pascal at the flow inlet of the artery, and show an average pressure exerted on the artery walls of 127,435 pascals. This is as a result of blood flow of high performance in athletes. The second simulation was a finite element analysis of an artery with endofibrosis. The aim of this study was to observe the geometry deformation in an endofibrotic artery. For this stage, the geometry was divided in three main parts: a hollow tube in both ends with the same dimensions and material properties mentioned before, with 50 millimeters of length that replicates the healthy part of the artery, was the two first parts, and the third part was a middle part of 40 millimeters of length that replicates the endofibrotic part with a Young modulus of 240 kilopascal, and a stenosis of 55% of its diameter, and we use the average pressure obtained in the previous simulation of 127,435 pascals as a boundary condition.
The displacements obtained from the FEA study showed that the diameter segments without stenosis increased from 15 millimeters to 23 almost 24 millimeters. As it was expected, the fibrotic segment did not experience a great displacement due to the stiffness of its composition. The study of the third stage was a computational fluid dynamic. The model of the CFD study consisted on the geometry obtained in the previous stage. The same parameters and boundary conditions as the second stage were applied. Results showed that the flow obtained in the end of fibrosis was turbulent after applying the same blood flow of 8 liters per minute. The geometry properties were an inner diameter of 12.56 millimeters, wall thickness of 1.78 millimeters, and a flow of 8 liters per minute as mentioned before. The arterial blood pressure was 200 millimeters of mercury plus the pressure atmosphere. Thus, along with the flow, when including the value of the pressure, the resultant trajectory of the volume flow went from laminar to turbulent. Also, the study revealed that the wall of the artery had two main significant changes. The first of them was the segment of the center that ended compressed as an oval-like geometry, while the segments at the ends remained as a cylinder but became thicker than the original geometry from stage 1. As the objective of the simulation was to calculate the final value of the flow, the use of the formula for volume flow rate was necessary with the velocity obtained from this study, which happens to be 0.0064 cubic meters per second. The simulation of the second stage recreated the pressure applied from the previous study of the artery. As a result, the stenosis did not show any changes of deformation in geometry, nor it expanded to a greater diameter. The reason is that due to the stiffness of its composition, the amount of pressure was not large enough to extend the diameter of the artery stenosis. Perlowski and Jaff describe in their study that the endofibrosis is characterized by the thickening of the intimal face of the external iliac artery, and it is commonly made of collagen fibers, fibroblasts, and smooth muscle cells, resulting in an arterial wall rigid enough not to deform. The blood flow in the simulation of the first stage was laminar. On the other hand, the study of the third stage regarding the blood flow was at first laminar, then through the stenosis, a higher velocity led to a turbulent flow. The behavior in this study was expected because when the diameter of the vessel narrows, a similar blood flow can only be maintained by an increase in flow velocity. The figures shown on the simulation of the first stage was the geometry obtained after the EIA study, and the deformation is observed as a result of the pressure that the modeled artery experienced. The diagnostic difficulty caused by relatively non-specific symptoms and the appearance of these only in high-performance exercising has previously led to the development of a detailed questionnaire to help discriminate vascular from non-vascular causes of leg pain in these athletes. The results shown in this study contributes in a visual way to the now used method to diagnose endofibrosis, resting ankle brachial pressure index, ABPI. This analysis is usually normal, but when ABPI is recorded within 5 minutes of ceasing maximal exercise, it may be possible to identify endofibrotic flow limitation with sensitivity and specificity of up to 100.
Results showed a turbulent blood flow that it is caused by the increased blood flow while exercising, and also because of the increased pressure in the stenosis segment. To obtain more accurate results, we suggest that more studies should be made by adding the force of a hypertrophied psoas muscle and applying a non-symmetrical stenosis in the simulation.